So today we get into our last couple of theorems that we are going to have to be worrying about throughout this entire year. Obviously we have a lot to learn, but in terms of the names of theorems and conditions you'll have to know on the AP test, this is it. So we've had the squeeze theorem, we've had the intermediate value theorem, we've had the extreme value theorem, and now we have Rolle's theorem and mean value theorem. Rolle's theorem is not really a biggie. I'm going to talk about it, but it's actually not even in the AP standards. And the reason it's not is because it's obsolete now. You have no idea what I'm talking about. But basically, once you learn mean value theorem, there's no point for Rolle's theorem anymore. It kind of encompasses Rolle's theorem. So I will talk about Rolle's theorem, but like I said, it's not one you're going to have to, I don't think they'll ever ask a question about it. You're never going to have to give it as a reason. But here's what it says. I was going to have this exploration be done, but I have changed my mind, and I'm just not going to. Hope you're okay with that. So Rolle's theorem says this. Okay, any theorem you talk about, you have to know the conditions that have to be met to use the theorem. And here are the conditions, first of all, that have to be met to use Rolle's theorem. Condition 1, you need a function that's continuous. Kind of move this so you guys can see it as I'm writing. You need a function that is continuous on the closed interval a to b. That didn't help at all, did it? So you need a continuous function. The second thing that has to be true, your function has to be differentiable on the open interval, a to b. And the reason we use open versus closed, first of all, you're never going to have to worry about open and closed intervals. You might have to write them as answers, but they'll never take off if you use open when you should use closed and vice versa. The main reason they won't is because they don't want to grade handwriting. If you're trying to rush and it looks like a parenthesis, but it's supposed to be a bracket, they don't want to make those judgments. And second of all, some textbooks have different definitions on when they should be used, and so they just don't want to get into all that. But you need you need a continuous function. It needs to be differentiable. And the third thing that has to be true is f of a has to equal f of b. That means the y values of the endpoints have to be the same. So to put that into, as an example on a graph, say I have two endpoints, the y values are the same, and I draw some continuous differentiable function. Doesn't matter what it looks like, so long as it has nice smooth curves right here. Okay. If you have these three conditions met, the conclusion is this. There is at least one c value, or x value, on the open interval such that f prime of c equals 0. So let you write that and then kind of put that in my own words. So there's at least one x value in the interval such that f prime of c equals 0. Basically, there's some point in the interval that has a horizontal tangent. There's at least one. If you start at a y value of, say, 2, and you end at a y value of 2, and your function is differentiable, and that part matters because let's say it wasn't differentiable, right? Let's say you had the same endpoint, and you drew a function that wasn't differentiable. Maybe it's continuous, not differentiable. There's no point along here where there's a horizontal tangent where the derivative equals 0. But if it's differentiable and nice and smooth, well, if you go up, it's got to eventually come down. Or if you go down, it's got to eventually come up. Or if you just went straight across and connected them, well, now every point, the derivative is going to be 0. This just says there's going to be at least one. So that's Rolle's theorem right there. So just really quickly, can we apply Rolle's theorem for the following graphs? Are all three conditions met? This one here, no, it's not differentiable. This one here, no, it's not continuous. Or you could say differentiable. I mean, as soon as you have one counterexample of why, you don't need to say all the reasons why. but nope. I should probably use good notation. I'm trying to rush through these, and I shouldn't do that. I should say, no, let's say these are all named f. F is not differentiable. Here, no, f is not continuous. And the last one, well, if you look at condition 3, the y values have to be the same. F of a has to equal f of b, and that doesn't happen here. F of a does not equal f of b. So no, Rolle's theorem cannot be used. Sorry, Rolle. Couldn't be used on any of these. All right. I was going to do this example, but because Rolle's theorem is kind of obsolete, I am just not going to, because a main part of this lesson, the main part, is the mean value theorem. This is probably, so, there are 4 theorems that you might have to state the conditions of on the AP test. You might have to recall by name. I would say 2 show up more than the other 2. I would say intermediate value theorem and mean value theorem are the 2 that show up more than the other 2. Squeeze theorem has shown up once in the last 10 years. And extreme value theorem, I think, was on a multiple choice at some point. So they don't show up very often, but mean value theorem is probably the main one that we do need to know. So here's the mean value theorem. Rolle's theorem leads into the mean value theorem. So I first want to draw a graph. And I'm going to draw a little function. Go ahead and draw this. And I'm going to label the endpoints A and B. Okay, so if I have this function here, and I found the slope from A to B. If I drew this line, it's called a secant line. If I drew the secant line and found the slope from A to B, that would be finding the average rate of change, right? If you find the slope from one endpoint to the other, that's finding the average rate of change. That's what slope is from one endpoint to the other endpoint. Okay. What the mean value theorem says is if you, and I'll write this out, but basically if you have a continuous and differentiable function, those are the only conditions you need. You don't need the y values to be the same. Okay, you need a continuous differentiable function. What it says is there has to be a point on this graph somewhere, there has to be an x value, where if you draw the tangent line to it, it's going to be parallel to the average rate of change, to the secant line. You can kind of see where it's going to be. I'm just going to wing it right here. Right around here, if I would draw my tangent line to the graph right there. Oh man, that was poopy. I apologize for that. That was supposed to be parallel. How about that? Is that better? But basically, there's going to be some point in the interval where the instantaneous rate of change, the derivative, is equal to the average rate of change. That's what it's saying. There's some point in the interval where the average rate of change is going to be equal to the instantaneous rate of change. Okay, so I'll just put this up here instead of rewriting it. That'd be silly. Work smarter, not harder. If I were you, I would write it, because the more you write, the more it helps remember, versus taking pictures or just not writing. That's not good practice. The more you write math, the more you retain it. So you can write this top stuff if you want. That's up to you. That's just what I've said in words. But the bottom stuff is what matters. The mean value theorem says if f is continuous on the closed interval and differentiable on the open interval, then there exists a number, c, at least one, in the interval, so not at an endpoint. You can't find derivatives at endpoints, such that f prime of c equals f of b minus f of a over b minus a. This notation is a little hairy, but it's kind of what I just said. The stuff on the right is the average rate of change, and the stuff on the left is the instantaneous rate of change. So there's some c value where the instantaneous rate of change equals the average rate of change. Mean, think about mean in math, means average. Like when you do mean, median, mode, mean means average. So that's how you can kind of connect average rate of change and instantaneous rate of change as you go through this. In fact, you already did a problem like this, I think, a couple classes ago with velocity. You probably don't remember, but there was a multiple choice. We did it as a warm-up. You had to find the t value where the instantaneous rate of change equaled the average rate of change. But that's the mean value theorem. And so why that makes Rolle's theorem obsolete, well, think about it. Rolle's theorem just says, I'll move this so you can rewrite if you're not done writing. But Rolle's theorem just says, if your y values are the same, then there's going to be some place where the derivative is 0. Like Rolle's theorem only works for an average rate of change of 0. It's saying there's going to be some point where the derivative equals 0. Mean value theorem is so much more beneficial because this applies to all average rates of change, not just 0. So mean value theorem encompasses Rolle's theorem. And that's why they don't even have it as a standard, because you can just use this one in place of it. All right, I'm going to move on to the last example. So if you want to pause this to finish writing that down, that is completely up to you. Almost just gave you the answer. All right. So they give a function on the closed interval 2 to 6. Find c such that f prime of c equals f of b minus f of a over b minus a. Basically, find where the instantaneous rate of change is equal to the average rate of change. And we know it's going to happen because this is a continuous function on this closed interval. The square root function is continuous on a closed interval. It's differentiable because there's no sharp turns or vertical tangent lines or anything like that. In fact, here's what the graph looks like. If I wanted to sketch, you don't have to sketch the graph on this one, but could. It's your square root function shifted right 2 units. Three, 4, 5, 6, 5, 6, 7, 8. So this is the graph. On the closed interval from 2 to 6, here's the graph. And we want to find the point in the interval where the average rate of change, so the slope from endpoint to endpoint, is equal to the instantaneous rate of change. So we have to find a few different things in this problem, and it doesn't matter the order in which you find them. You're going to have to find the average rate of change, like you're going to have to find that value, and then you're going to have to find the derivative of this function, and then set them equal. Like that's the whole idea. So first, let's find average rate of change. And so the average rate of change is your slope formula, f of b minus f of a over b minus a. So if I plug 6 in, we get 2. If I plug 2 in, we get 0. So those are my y values over 6 minus 2. So 2/4. 1/2 is the average rate of change. That's the slope that connects one endpoint to the other endpoint. That's the slope of the dotted line. And I'm trying to figure out where would the tangent line be parallel to that? Where does it have the same slope? It's right there. I just eyeballed it at right around 3, maybe a little less than 3. That's just from eyeballing it. Let's see how good I am. So now we have to find the derivative of the square root of x minus 2. So I don't like square roots when we're dealing with derivatives. I like powers because we have our power rule. So I'm going to have to do chain rule here. You could forget chain rule and get this right because the derivative of the inside is 1, but I always like to have that on my mind, even if it's not going to matter, because you could luck into getting the right answer here. So chain rule, derivative of the outside, inside stays the same, times the derivative of the inside, which is just 1. So it doesn't come into play, but don't forget about it. Okay. And we could write that as 1 over 2 radical x minus 2. That's the derivative. So the question is, where does this derivative equal this average rate of change? Where are these two things equal? That's what we're trying to find. So set them equal. You can cross multiply this bad boy here. You can divide both sides by dose. You can do a little square both sides. And then add 2. Ha! I was right. My eyeballs are perfect. I eyeballed right around 3. It was 3. I also had the answer key right next to me, but don't tell anybody. All right. So that means when x is 3, the average rate of change will be equal to the instantaneous rate of change. Okay. I would pause this, and I would like you to try example 3 right here. Give it a shot, see how it goes. Find C that satisfies the mean value theorem. What that means is find the C value where this derivative is equal to the average rate of change from -1 to 1. Pause it and try it. All right, welcome back. I'm sure you all paused it and tried it. I'm just going on the honor system. Here's your work. Here's your answer. First thing you had to do is find the average rate of change by finding your y values and doing your slope formula, -1. Find your old derivative, quadratic, so set this equal to 0. You could use quadratic formula or factor, whatever the case may be, but you get 1 and -1/3. Here's where you need to be careful. This only guarantees C values on the open interval, not at endpoints, because you can't differentiate at endpoints. So, throw 1 out the window. 1 is at an endpoint of the interval. So -1/3 would be your answer. And that is in the interval. All right. Let me know if you guys have any questions whatsoever. And peace out. Home slice.